Last time when we were talking about friction, we were talking about the situation where we had a level, that don't look too level, but let's say it's level. We had a level surface and we had a 10 kilogram crate sitting on that floor. And we said we had the weight of the object, which was the force due to gravity. So we called it the weight, and we said it's the force due to gravity, and that's the mass times acceleration according to Newton's second law. But this acceleration here had a special value if we're talking about gravity, where A will equal 9.8, so we gave it a little g. All right, and this little g, so little g was 9.8 meters per second squared. So in this case, we said that the force of gravity was our mass, which was 10 kilograms, times the force of gravity, which is 9.8 meters per second squared, which was then 98 kilograms times meters over second squared, which was 98 newtons, because a newton is a kilogram times meter per second squared. That's the unit for the newton. So we had the force of gravity, or the weight down, of 98 newtons, and then we says we had a reaction force upward of the floor. Basically, the floor is pushing up on the crate, and that is the normal force. And we said if everything was balanced, the normal force would have to be 98 newtons, equaling the force of gravity, so that everything stays nice and balanced and in equilibrium. So the net force in this case had to be 0, so that you didn't have any motion up or down. So the vector force upward is equal to downward, and we solved that kind of problem. And we talked about the force of friction. We said the force of friction, static for no motion, was equal to this coefficient of static friction times the normal force, so that the force of friction was directly proportional or related to the normal force. So the greater the normal force, the greater the force of friction. Now what I wanted to show you here in this situation was that by raising up the floor for this 10 kilogram crate, we were going to effectively reduce the normal force and hence reduce friction. So let's do this. Let's do our free body diagram in this situation. So we're going to think of this, you're going to have weight downward. So this is our weight, and let's say this is 98 newtons down. That's the force of gravity. Then I think last time we had in blue, we said we had the normal force, and this is normal or perpendicular to the plane that the object's resting on. So the object's here on an inclined plane this way, and the normal force is going to be upward, shown in blue. And then we have a force of friction, and if the object wants to go down the hill, so as to say, then the force of friction, which I'm going to put in red, is going to be up the hill. So there will be a force over here of friction. All right, so those are our three forces, and that's our free body diagram. Now the next step is to draw a little axis through the normal vector. So let's do that. Let me see if I could make this axis for you nicely. See what I'm doing here? I'm making a coordinate axis that's kind of like that. Okay, good. So that worked. That's in green. Perfect. Now let's take a look at what we have here. We have the force of friction in red, which is going in this direction on the green axis, which is kind of like, I could say almost that this is like the X and almost like the Y axis that's just rotated a little bit, right? And the blue normal force, which is coming from the floor pushing up on the crate, or the plane pushing up on the crate, is on the Y axis here, the rotated Y axis. And now look at the weight. Look at the yellow vector. The yellow vector, notice, does not have itself situated nicely on the green axis. If it did, then we'd have all perpendicular vectors, and we could work very nicely with that. So what we want to do is we want to get this yellow vector, resolve it or show its components on the green axis that we drew. Now in order to do that, we need to know one thing. We need to know what this angle over here is, and I'm going to tell you ahead of time that this angle right in here is 30 degrees. If this angle's 30, then what you have right in there is a 30-degree angle. And the reason for it, I could show you just carefully here. This is a right angle right there. So we have a 30, 60, this is 60, 90 right here, triangles is 30, 60, 90. Since we have an axis here that's two perpendicular lines, if this is 60 degrees, then this guy in here has to be the 30. So whatever this is over here on your plane, if that's 30, that angle right in there is going to be 30, and that's just a little bit of geometry to see that. So now that we have that, what we're going to do is try and resolve our yellow 98 vector into two components along the green axis. We're going to put one component here, very carefully, and the other component here. All right, so I took this yellow and I turned it into two components, two pink components. This guy over here is going to be 98 times the cosine of 30 degrees. And this guy over here along the plane downward is going to be 98 times the sine of 30 degrees. Now how is that? Well, just as a little sidebar over here, if I rotate this whole axis, and I'll do it in green, I think, just so that you see what's going on. Here's the green axis that we have, and we have that yellow vector kind of like coming out like that. And this we said was 30 degrees. So if we have something like that, and of course this whole thing, this whole axis is rotated that way to look like that, then we can say that we have this guy is going to be whatever this is. This is our so this is our 98 newtons. So this one here will be the 98 then times the cosine of that angle 30, and this guy over here is then 98 sine of 30 degrees. That's just taking the vector and resolving it into two components. So we've done that, and if we do that, then this over here will equal, let me see what I got for that. I think it's 85. Yeah, this is 85 newtons, and this one over here is 49. So this is 49 newtons. And that's it. Once that happens, that yellow 98 vector can go away because I put it into two perpendicular components in pink. And we've got 1, 2, 3, 4 force vectors to deal with. So let's look at the y axis here on green. And in that case, we're going to look and we're going to see that the blue normal force has to be equal to the downward pink force, which I'll show here, of 85 newtons. So this here guy in blue, that is not Newton, that is the normal force up here. So that's 85 newtons. How did I know that? Because the forces up have to equal the forces down, otherwise the block would be flying off the plane, and we know it's not doing that, it's sitting flat on the plane. So we have an equilibrium situation along this y direction here. What about these two guys here? Well, we have force of friction going upward. So this force of friction is up. Down, we have this pink minus 49 newtons. And we know that whole expression, this force upward minus the downward force, because we're saying here now that up is positive, is going to be equal to this here then is the net force along the plane. So the net force along the plane has to be equal to the mass of the object times the acceleration along the plane. All right, and in this case, how do we know what this force of friction is? Well, let's see if we could determine the force of friction. So the force of friction is equal to this coefficient mu times the normal force. The normal force we said was 85. So assume, let's say it's moving, the object's moving, so we're going to call this kinetic. We're going to call it kinetic for moving, so it's force of kinetic friction, which we talked about last time. And let's just give this a number. Let's say that this is 0.2, say, for example. And this guy here is the normal force. We said that was 85 newtons from up here. It's 85. So this force of friction then is going to be 0.2 times 85. And I don't have a calculator just handy on me, but I will tell you that this number here will be less than the 98 newtons that we had over here when it was flat. Okay, so we have the force of friction upward. It's going to be a small number. This 49 is going down. It's going to be a little larger than the force of friction. And if we subtract those two, we're going to get mass is 10. So this, I'm probably confusing you already. This is going to be 10 kilograms. There's going to be some acceleration down. We could figure out this force of friction, whatever it is, this number here. Figure out what this is, and then we could find the acceleration. So that was the problem of the plane, the block on the plane. And what I really wanted to just show you here was that by raising the floor upward through an angle, it reduced the normal force. And that kind of makes sense, because as the floor raises upward, there's less and less pressure of the floor, force of the floor on the object, till actually the floor goes up vertical and there's no force at all and the object falls straight down. All right, so that's kind of what we wanted to show and to demonstrate, and I think that we've done that. So we'll talk next time.